Today's video is going to cover section 3.2 day 1, so we're going to be talking about differentiability. So we're going to talk about what it means for a function to be differentiable at a point. So today we're going to be talking about one-sided derivatives. So our first point here is, since a derivative is a limit, we can look at one-sided derivatives just like we will look at one-sided limits. Right? So we've looked at one-sided limits with our left and right hand before, so now we're going to be doing the same thing with derivatives. So the right-hand derivative of a function at a point A is just defined as the limit as x approaches a from the right of f of x minus f of a over x minus a. So we're still using our limit formula for the derivative at a specific point, but now we're just looking as we approach that point from the right. So in our example here, if we're calling -2 as our a, right, as we approach from the right, we'd be coming to a from that side, from the right side. So very similarly, if I want to talk about the left-hand derivative, the left hand at a point A is just defined as the limit as x approaches a from the left of f of x minus f of a over x minus a. And again, we're using our formula for the derivative at a specific point because we're looking as we approach a specific value from the given side. And so here is where we would be approaching that value of a from the left. And we can see these are kind of piecewise defined functions, so we can see how those limits would be affected coming from the left side versus the right side. So the important thing to note here then is the derivative exists if and only if the function's left-hand and right-hand derivatives are equal. Okay, so we're saying a derivative at a point exists only if the function's left-hand and right-hand derivatives are equal. I also want to make note, right, our big idea here is that a function is only differentiable at a point if and I'm going to use a little shorthand here, if the left-hand derivative is equal to the right-hand derivative at that point. So we can talk about the derivative existing at that point. We can also talk about the function being differentiable at that point. And that's what we're going to be looking at today, deciding how we know if a function is differentiable at a point or not. Okay, so when we flip over here, we're going to look at 4 cases where we're going to have a problem with our function being differentiable. So I got to play with the zoom here a bit. It's not too bad. Okay, so our first problems with a function being differentiable are going to be points where we have what we call a cusp or a vertical tangent. And you can see examples of those types of issues here. And so the important thing to note is that anytime we have a function with a rational exponent, okay, it will have a vertical tangent or a cusp. Therefore, there's always going to be one place where the derivative does not exist. So if we look at these 2 examples, or this one example, it says find all points in the domain of f of x equals x to the 1/3 where f is not differentiable. So if we think of that graph, we know that it looks like this. And so here at x equals 0, we can see we have this vertical tangent. So we know this is not differentiable at x equals 0 because of a vertical tangent. Now, the other example I want to add that's not in here is I want to look at f of x equals x to the 2/3. If we graph that function, we get something that looks like this. And I just want to point out there, that would be an example. Again, we're not differentiable. At x equals 0, but this time that would be an example of a cusp. So again, we run into these anytime we have a rational exponent in our function. So those are our first two problems with differentiability. Okay. The next kind of issue we can encounter with differentiability is something where we call a corner point. And you can see that illustrated in the graph here, where it comes to that V shape we call it a corner. And this is going to happen anytime we have an absolute value function. Okay, so anytime we have an absolute value function, it will have a corner. Therefore, there will always be one place, again, where that derivative doesn't exist. So for example, my question asks me to find all the points in the domain of f of x equals the absolute value of x minus 2 plus 3 where f is not differentiable. So using what we know about translations, right, our parent graph is the absolute value of x, and we know this is translated to the right 2 and up 3. So if I just quickly sketch that out, I know I went right 2 and up 3. Then I know I have this graph here. And so looking at my graph, I can tell then that f of x is not differentiable at x equals 2 because that's where my corner is. So I'm not differentiable at x equals 2 because of a corner. Sorry, I know that went off the page there. Okay. Now, the last place where we're going to have a problem with our function being differentiable is anywhere there's any kind of discontinuity. So as soon as we have a discontinuity at a point, we're also not going to be differentiable there. So we need to watch for this, just like we were talking about with continuity. We need to watch for discontinuities when we have a piecewise function or a function that might have a vertical asymptote. So as soon as we know that a function is not continuous at a point, we automatically know that it's not going to be differentiable at that point. So for my example, it's asking to find all the points in the domain of my piecewise function where f is not differentiable. So if I'm looking at this, my guess is that I'm going to have a problem with continuity at x equals 3. So I'm going to check really quick to see if it is continuous there. And we know to be continuous, my left hand and my right hand limits have to be the same. And it also has to be equal to the value of the function at that point. So doing a quick check, I know that my limit from the left would be 3 minus 2, which is 1. My limit from the right would be 4 times 3, which is 12. And my function value also happens to be on this piece here, so 1. And pretty clearly, we can see that our left and right hand limits are not equal to each other. So that is discontinuous at x equals 3. So I'm going to say f of x is discontinuous at x equals 3 because our left hand and right hand limits do not agree. So we could say, therefore, it is not differentiable. So that discontinuity causes it to also not be differentiable. Okay, and then my last example here, find all the points in the domain of my function f of x, my rational function, where I'm not differentiable. And again, right away I'm thinking about where there might be vertical asymptotes. So I'm going to go ahead and factor this. And let's see, x minus 3 times x plus 1. So I know f of x is not differentiable at x equals -1 and 3 because of a vertical asymptote. So again, those are the 4 types of issues we're looking out for when it comes to differentiability. We're looking for those cusps or vertical tangents, with rational exponents, corners with absolute value functions, and then any function that's discontinuous at a point is automatically not differentiable at that point. So now we're going to look at some graphs and make sure we can pick out these issues on a graph. So I'm going to turn the page. Get my notebook turned the right way. Here we go. Okay, so all I want to do right now is, looking at these graphs, identify places where the derivative wouldn't exist. So I'm looking for these cusps, corners, vertical tangents, or anywhere there's a discontinuity. So to explain, we're just going to classify what the problem is with the graph. So as I'm looking at this graph, the first problem I see is at x equals -2. I know the derivative would not exist there because I notice that I have an infinite discontinuity. Right, I have a vertical asymptote. And again, I know that if I'm not continuous, I can't be differentiable at that point. The next thing I notice is that x equals -1. And I see how it kind of comes to this point here. That's an example of our cusp. It's not quite so much a V as the corner, but it still comes to a point at x equals -1. At x equals 0, I notice I have a vertical tangent. And then the last problem we have in terms of differentiability is going to be at x equals 2. And we have here a removable discontinuity. So again, I'm not continuous, so I cannot be differentiable there. Okay, I'm going to skip the graph below here. It's actually the same graph, and it's asking us the same questions. So we already know we're not going to be differentiable at the values that we identified, and other values, all other values in the domain of that function, we will be differentiable. So let's go ahead to wrap this up. On page 17, want to see how we handle this now if we don't have a graph, but we have an actual function. And so my question says to show that the following function has left-hand and right-hand derivatives at x equals 0, but show that the function is not differentiable there. So we know to be differentiable, right, 2 things have to be true. My left-hand derivative has to be equal to my right hand. So let's go ahead and calculate our left-hand derivative. So I know my left-hand derivative is going to be the limit as x approaches 0 from the left of f of x minus f of 0 over x minus 0. So we can go ahead and figure out what this is. I'm keeping my limit notation. F of x I know is x squared. F of 0 is 0. And on the bottom I just have x. So this is going to simplify to x squared over x, which is the same as the limit as x approaches 0 from the left of x, which we know is equal to 0. So now my left-hand derivative is 0, and so now we're going to check on our right-hand derivative. So now we're going to take the limit as x approaches 0 from the right, still f of x minus f of 0 over x minus 0. But now my f of x is 2x. F of 0 is still 0. And again, on the bottom, I just have x. So now I have the limit as x approaches 0 from the right of 2x over x, which just simplifies to 2. So my limit from the right-hand side is 2. So now we know our left-hand derivative is not equal to our right-hand derivative. So we would say that y is not differentiable at x equals 0 because my left-hand derivative is not equal to my right-hand derivative at x equals 0. So while those left and right hands exist, since they're not equal, we are not differentiable at that point. So number 2, we would follow the same process. So now we're looking if we're differentiable or not at x equals 1. So again, we're going to follow the same process. So for my left-hand derivative, I'm going to check the limit as x approaches 0 from the left of f of x, I'm sorry, not 0, that would be 1 from the left, of f of x minus f of 1 over x minus 1. And we'll do the algebra. I have x squared minus 1 over x minus 1. Now I see I can factor my numerator. So I have x minus 1 times x plus 1 over x minus 1. So my x minus 1 factors cancel. I'm left with the limit as x approaches 1 from the left of x plus 1. And so I know my left-hand derivative is 2. So now we'll check our right-hand derivative. So now I'm approaching 1 from the right. So if I approach from the right, now my function is 2x minus 2 over x minus 1. And so I'm going to factor out a 2 of my numerator. And I now have that factor cancel. And so my limit as I approach from the right is 2. So in this case, because my left-hand derivative is equal to my right-hand derivative, I know that my function y is differentiable at x equals 1 because my left-hand derivative is equal to my right-hand derivative at x equals 1. So in today's practice, you'll be working with both functions and graphs of functions to determine whether or not they are differentiable at a point.